Good morning and hello everyone, and welcome to the next class for the classical mechanics course. And today we'll be continuing from the next lecture that if you remember, we were doing this conservation's laws. So in the previous class we did the conservation of the linear momentum when your system was being translated from one position to the another position in the configuration space. Now that was the condition that when your coordinate, which was cyclic or ignorable coordinate, and that is not absent in the Lagrangian, that is absent in the Lagrangian. So then if the system is being translated from one position to the another position in the coordinate space, you have that the corresponding conjugate momenta that for this coordinate which was absent or cyclic coordinate is going to be conserved quantity. And in the same way, we are going to learn about this angular momentum, that if you consider a system, the Lagrangian defined by the coordinate, which is defining the rotation of the system in configuration space. So if your system rotates from one position to the another position, and the rotation coordinate is your qj, that is naturally going to be the theta in that case, and then d theta or dqj correspond to the rotation of the system of the particle around some axis. That is the rotation from one position to another position is denoted by this dqj. So system is rotating from, and this is from this position to this position, and that is by this angle dqj. Okay, so as we have already studied that put in condition that velocities are not affected by the shift in the origin. So one of the Cartesian coordinate of the center of mass of the system is if you consider is that when you translate or rotate, that is center of mass velocity is not going to affected by the rotation. So you demand that this t is not going to be affected by this rotation. Delta t by delta qj is going to be 0. So that means we are not kinetic energy independent of this coordinate. Further, we will assume for the conservative system, naturally we are right from the beginning we are considering the conservative system for which the potential is independent of the velocity of the system. So that's why when this potential is independent of the velocity of the system, you know that if this is my Lagrange equation, then this Lagrangian is difference of kinetic energy minus potential energy. This is how you define. And if my this del V by del Q dot is going to be 0, because the potential is not a function of q dot, the generalized velocity. So this part is not going to contribute here. Okay, so this part is not going to contribute here. So you have d dt of partial derivative of kinetic energy with respect to q dot, and similarly you demand that this velocity is not being affected by this motion of this coordinate. So this part here is not going to contribute with respect to the qj. So sorry, this kinetic energy is not going to contribute with this because of this equation, this demand. So my Euler equations now is this thing. Okay, so from this part, time derivative part, the potential velocity potential is not there, and from this position derivative part, so kinetic energy is not there. So this is my, so if I take this dv by dt this side, it becomes negative del v by del qj, and this we know that is equivalent to the generalized force. Okay, because if my system is conservative, then the force can be written as the gradient of the potential which is so that means my force can be derivable from the scalar potential. Okay, that is what I have. So this is equal to what I told to you, that is yeah, this become equal to Qj, the generalized force. And you know the generalized force, how you define the generalized force is a force forces which are acting on the system, and this is the forces which are acting on the system, and then the delta R by delta Qj. So now we our motive is to find out what is delta R by delta Qj. That means if the system is rotating, then what is delta R by delta Qj. So if you see here, since this delta Qj here is representing the rotation, infinitesimal rotation of the vector R, this vector R, this is my vector Ri, and from this position to this position it is rotating. So delta is Qj is this is how much it rotates. The magnitude of the derivative is given in the figure. You can see that this magnitude, this delta Ri, this is what delta Ri is basically this, what is this, and then this is this angle dqr. Okay, so what is this thing? What is this one? This one is because this angle is theta and this is r, this is r, so this is naturally going to be r sine theta, and then multiplied by this rotation angle. The radius of this is r sine theta, and this multiplied by this angle, this is delta Qj, is going to give me this arc, that is delta Ri, magnitude of this, and then I can write delta Ri upon delta Qj is going to be Ri sine theta. So we're talking about the magnitude and not talking about the direction here. So naturally its direction is going to be perpendicular to the both Ri and n, so that's why delta R by delta Qj, this direction of this is going to be n cross r. Okay, so n is basically the perpendicular to the plane in which n is perpendicular to the plane, and this is delta Ri. Okay, so this is Ri and delta Q. So this is straightforward. So Ri is this, okay, n is this. So this is if you take the component of r in ni, it's going to be perpendicular. Delta Ri upon delta Qj is going to be perpendicular. Next, if I move that, and then I have to find this, then what is Fi? So if I going to put this cross Ri into here with this F dot, so that this, what I'm going to get is nr cross Ri is so because this is a unit vector, so I can take this outside, and then this becomes r cross f, and r cross f is nothing but you know, it is the torque. R cross is the torque. So Qj is the torque acting in the direction of the n. So Qj is basically giving you the component, because j is, there are many Qj's, Q1, Q2, Q3, depending upon what coordinate you are choosing. So this is representing that the component of the total applied torque n about the axis of rotation in the direction of n, that is n is the axis of rotation. So this we have find as what is my Qj. Now the kinetic energy, now let us define the kinetic energy, because what I have is the relation is d dt of this. So I have to find this delta t by delta Qj and take the time derivative and equate it to the generalized force what we have found. So the kinetic energy is half mi ri dot square, because this is velocity square. So and then so if you remember, we have d dt of delta t by delta q dot, and then this is equal to my Qj. So this we have figured it out, and then we have to find it, what is this thing. So for that we have find dt by delta Qj dot, this is going to be the generalized momenta Pj, because you know how you define the generalized momenta. Generalized momenta is Pj is delta L by delta Qj. but because delta L by delta Qj is, this is T minus V, and we have delta Qj dot, so but the delta V by delta Qj is going to be 0, so this is basically delta T by delta Qj. So this is going to be the generalized or conjugate moment in our case. So now let's do this. T is MIR square. If I differentiate with respect to Q dot, so this is going to be twice Ri dot. So this is going to be twice Ri dot. Mi is constant, and then delta Ri by delta Qj dot. This is straightforward. So I can have this MIRI, and then this dot product with delta Ri dot upon delta Qj, because if you see, we have already proved that this delta R dot upon delta Qj is going to be delta R upon delta Q. So we had already proved it in earlier lectures. You can go and see that, and when we're defining the generalized coordinate and generalized velocity, so I, in place of this, I can put this delta R by delta Qj, and because we have delta R by delta Qj as this, we have n cross R. So this is MIRI dot, and this dot product of this n cross I. Okay, so this is again, this is the unit vector. I can take to this side, and then this is my MV, and this is R. So this is going to be the R cross basically MV. So this is P. So naturally it is going to be my angular momentum. Okay, so this is Ri, and this is Ri dot. This is nothing but Ri dot. So this is MVI, and then this is N is outside because this is unit vector. So this is R cross P is going to be my linear angular momentum. So this Pj basically, Pj is what? This is Pj is dt by del Qj dot. Okay, this is we have calculated. So this is going to be the angular momentum which is acting on the system, because of which it is rotation or angular momentum of the rotation. So this is going to give the component of the angular momentum or the direction of the rotation of the body. And what we have is that our equation of motion was that, if you remember, this is what d dt by dq is Qj. So that is d dt of the t by delta Qj dot is equal to Qj. So and this is my Pj. This is, we have already covered it. This is my Pj. So this is d dt of this is d dt of Pj, and this is going to be equal to Qj. So if I equate this, and we have already figured out the force is nothing but the torque in the direction, the total torque in the direction of the rotation, and then and then this is what Pj is my angular momentum. So this is d dt of Pj, and is going to be 0. Okay. So this is basically L and N is going to be constant. So this tells you about the conservation of the angular momentum. If the total torque is going to be 0, this has to be N, not T. If the total torque is along the rotational axis vanishes, then the angular momentum is about the axis of rotation in the direction of N is going to be conserved quantity. But you started with that the Q V is the potential, scalar potential of the system is independent of the velocity, coordinate, generalized velocity and time, and then this is that kinetic energy is not depending upon the generalized coordinates. So that gives you the conservation of the angular momentum. So let's now moving further, the third conservation is the conservation of energy. That is the conservation of energy means what we have energy is the Lagrangian is Lagrangian is giving you the energy component, that is kinetic energy minus the potential energy and scalar. quantity. So if your Lagrangian describe a closed system that it is not interacting with anything outside, what is happening with the system is like there, and so it cannot depend explicitly of time. So then I have my Lagrangian is delta L by delta t, that is for the conservative system. So, or if the system exists in a uniform force field, so that's not going to be affected by the time, the Lagrangian of the system. So that equation of motion is not going to be affected by time. So when this is there, so let us try to write the total derivative of the Lagrangian. So because L depends upon Lagrangian depends upon this generalized coordinate, generalized velocity, and the time. So that if I write the total derivatives, this is dl by dt. So because L depends upon q, so first we partial derivate with L with respect to q, and then we derivate q with respect to t. So when you derivate this q with respect to t, so this is going to be q dot. So this you have q dot here, and then similarly you have to differentiate L with respect to q dot, and then q dot with respect to t, that is delta q dot with respect to delta t, and this is going to be my q double dot. And then you have the term that sum over j, that is delta L, because if delta L by delta t and delta t by dt, so this is going to be 1, and this is already 0 because we have considered that my Lagrangian is independent of time. So but anyhow, if you are differentiating doing the total derivative, so this component is there, but that is by demand is going to be 0. So and we know that our Lagrange equation of motion, that is d dt of this is my Lagrangian equation of motion, that is d dt of if you remember, that is delta L by delta q minus delta L by delta q is going to be 0. So this is my Lagrangian equation of motion. Now what I am going to do is I am going to use this delta L by delta q here in this equation. Okay, fine. So now I am going to write this dl by dt is for that, if you see that we have q dot j, and in place of this I write d dt of delta L by delta qj. So this is q dot, and I have written this as d dt of delta L by delta qj, and the second term is as such. So now I can write these if you combine these two terms, so then you can write this is d dt of q dot delta L by delta qj. So because this is first term and this is second term, differentiation you keep first term constant, differentiation of the second term, this is what to have d dt of delta Lq, and then differentiation of the first term, this is what you get q double dot, and then keeping second term constant, which is what you have. So this we can write as total time derivative of this q dot delta. And then this is d by dt, and this is d by dt also, so I take it common, so this is going to be L minus this whole quantity. So you see that this quantity is equal to 0, the time derivative of this quantity is equal to 0, that means this quantity is going to be a constant. Okay, so let's put this constant as equal to minus h. Okay, so this quantity is some constant, this is minus h, this is some constant. And if u the potential, which is u does not depends explicitly on the velocity or the time, so then this is then you have del u by delta q dot is going to be 0. So if I put here in this case, so delta L by delta q dot, which is here in this case, so this L is t minus u, and this u is independent of the velocity, you have dt by dt qj. So in this equation, this is L minus q delta L by qj, this is my equation is L minus sum over j q dot j delta L by delta q dot j, that was minus h. Okay, so in place of h I write the kinetic energy minus the potential energy here, and then q dot is q dot, and L, because the L contains from dl with delta dq dot, that is potential is velocity independent, so I have dt by dq dot j, and this is going to be h. Now what I'm going to apply is that if you remember when we did this kinetic energy in terms of the generalized coordinate. So if you remember this, the total kinetic energy comes out to be, that is some three terms, m naught, mj and mjk. If you go to the previous lecture, then you see that the kinetic energy will have three terms, that is, this is independent of q dot. Okay, this was depending on q dot. So there was no q dot term, and there's one q dot, and then you have two q dot quadratic terms in q dot. Okay, so this was you're having, and then if you demand that the system is scleronomic, so for a scleronomic system, that is that it doesn't depends upon time, independent of time explicitly. So if you demand that delta r by delta t equal to 0, so in that case you see that if you remember, m is 0 and mj is 0, because this term was both present in m naught as well as in mj. So only the kinetic energy term which survives, that was mj k. Okay, and that is with these two terms qj and delta 2k. And then another theorem, that was the Euler theorem, which says that if I have some function, so if I say some function that, if you remember, this is Euler's theorem, that if I have some function, say some function f which depends upon some yi, and this is of any order, so then and this is, if this is homogeneous, so then this is can be written as, this is sum over I, and then I have yi and delta f by delta yi equal to n times the function, where n is the order of the function. What is the order of the function? The same situation is here, is what I am going to have is here, this, if you see this term here, T is my kinetic energy, and this depends upon this q dot. Okay, so, and this is of second order, because for this scleronomic system, this is what I having is the survival term is, this is depending upon q dot square. This is of second order. So for this if you compare with this, so this can be written as this q dot, this which depends upon the function q dot, and then function this is going to be 2 times the t. Okay, because you see whatever the function, depending upon whatever the variable it is depending, then this is going to be the n times that function. So because the order is 2, so this n is going to 2, and this is the function is my kinetic energy is 2t. Okay, this is going to be 2t. So now I can this is my t minus v, and this is going to be 2t and minus h. So this is t plus u is because 2t minus 1 is t, and this if you see, if you take the common negative, what you're going to have is kinetic energy plus the potential energy is going to be something which is h we define as, this is going to be the constant, which is the total energy of the system. So you see one difference here, so my Lagrangian was t minus u, and this quantity h which we are defining is as t plus u. So this is going to be another definition, and that is known as the Hamiltonian of the system. Okay, so this is what we have for the total energy. So this function h is we'll call Hamiltonian. We we will define it into the coming lectures. Next lecture of the system. This is Hamiltonian of the system, and may be defined as this is going to be H is T plus U, kinetic energy plus the potential energy, as the Lagrangian is defined as the kinetic energy minus the potential energy. Okay, so it is important to note that when you demand that the Hamiltonian or what this quantity is equal to the total energy, but there is two condition has to be followed. So one is that if you write the transformation equation, this is Ri is going to Ri to the U coordinate, Qi, Q dot I and T, where I going to 1, 2, 3 and minus K, depending upon what is variable. So when this Ri ensuring that must be independent rectangular coordinate or generalized coordinate must be independent of the time. Okay, so that's why then the delta T by delta Q is going to be 0 as we have demanded. The second thing as is you see that we demand is that is going to be 0, and then the potential energy must be velocity independent. So the potential is V is not depending upon, so V is not, U is not depending upon Q, this is only depending upon Qi, this is not depending upon Qj, so this is going to be 0. So under these two conditions, that my Hamiltonian is going to be constant and that is going to be total energy. But the question is that does this Hamiltonian is equivalent to the total energy of the system? And the second question is the energy is conserved for the system. So these two are different things. But most of the cases, the Hamiltonian of the system is going to be the total energy of the system, most of the cases. But it's not always there. But the energy is to be conserved for every system. Okay, so these two questions has to be considered separately. So the concept should not be mixed. So whether the total Hamiltonian is going to be the total energy of the system, and the Hamiltonian is conserved, so that is the total energy conservation of the system. Okay, so I'll stop here this lecture, and then the next lecture I'll continue from here about this. So probably I will start the Hamiltonian dynamics, and I'll because I have built this the concept of Hamiltonian, that is expressed as the total energy, kinetic energy plus the potential energy, as the Lagrangian is kinetic energy minus the potential energy. Thank you very much.